Hello everyone, this is the final video walkthrough for my Mysh project, a custom shell implementation in C. In this video, I will demonstrate compilation, background process management, and walk through the code for signal handling and client message reception. First, let's compile the code from scratch. So we have to open a terminal, go to the source folder. Now, I'll remove any existing object files and executable by doing make clean. Great. Now I will compile all the C source files using GCC in the makefile. As you can see, the project compiles successfully without any warnings or errors. Okay, now let's demonstrate the background process management. Let's go to the program first. Mysh, and then let's do sleep 100, make it background. And then as you guys can see, we have the PID visible to us of the sleep 100 process. Let's do another one, sleep 200, make it background. And we can see the PID of the sleep 200 again visible to us. We can also use the PS built-in function to show all the background processes and their PIDs. So as you can see, it is matchable. Now, let's terminate the sleep 100 by using the kill command. We do kill and the PID of the sleep 100, which is 1109984. And now we get the message done. Once we get this message, it means that the process sleep 100 is done and is terminated. And if we do PS again, we can only see the sleep 200 PID available. Now, let's wait for the sleep 200 to end by itself, naturally. Okay, now we can see the done message for the sleep 200 background process. And now if we do PS again, there is nothing shown because there is no background process remaining. So the background process management, listing and killing and notification system is working as expected. Now, let's look at the code that handles signals and done messages. The core is the sigChild handler function in Mysh.c. This handler is triggered whenever there is a child process which its state has changed. In another word, when it is terminated. Inside the handler, we use a while loop with await PID -1 ID of the status and W no hung. The -1 waits for any child and W no hung is crucial because it makes wait PID non-blocking. This prevents the shell from freezing even if the signal arrives with no children that are actually terminated yet. The loop reap all terminated children in one go. For each of the child PIDs, we search our BG process array, to find the corresponding background job information. Instead of printing directly from the signal handler, which is unsafe because printf and display message, which users write, are not fully async signal safe and could interfere with ongoing IOs. We format the done message using sprintf into a buffer array called BG completion messages. We store these messages temporarily. After buffering the message, we remove the completed processes from our BG process tracking array and decrement the background process count, which is BG count. In the main function, we set up this handler using sigauction. We use SA restart to automatically restart interrupted system calls and SA no cold stop, so we only get signals for termination and not for stopping, for example, Control Z. Now, how do these buffered messages get displayed? Back in the shell loop, while one in main, which is over here, just before we display the prompt Mysh, we call print buffered messages. This function iterates through any messages stored by the sigChild handler in BG completion messages and prints them using display messages. It then clears the buffer count. This ensures done messages are printed reliably between commands, minimizing interference with user input and the prompt. For alternative approaches, we could have considered printing directly from the signal handler, and the reason we didn't choose it was because this is unsafe due to the non-reentrant functions like printf or even write, potentially interrupting themselves or other standard IO's operations, leading to corrupted output and deadlocks. Another alternative is using a pipe or self-pipe mechanism. This signal handler writes a byte to a pipe, and then the main loop uses the select to monitor the pipe along with the STDN. The reason I didn't choose that it is because even though it is safer than direct printing, this adds complexity to the pipe setup management and integrating it into the main loop's input handling. Current approach of buffering messages in an array and printing them at a safe point in the main loop is a good balance of signal safety and implementation simplicity for this shell's requirements. Okay, now let's examine how the chat server handles incoming messages from clients, particularly focusing on potentially long messages. The relevant constants are in socket.h. Primarily, we're looking at buff size, which defines the size of the pre-client input buffer. In the server's main loop, run server in chat server.c, select tells us which sockets have data. When a client socket is ready, we call read from clients. Read from clients in chat helpers.c essentially calls read from sockets in socket.c. Inside read from socket, the read system call attempts to read data from the socket into the client's specific buffer, which is car.buff. Most importantly, it reads at most the amount of space remaining in the buffer, which is buff size minus inbuff. Inbuff tracks how much data is already in the buffer from previous reads. For handling long messages, if a client sends a message longer than buff size, the read call will fill the buffer partway. Read from sockets then checks for a network new line, which is \r\n using find network new line. Use a function over here. If a new line is found, it indicates complete message or end of the one is in the buffer. If no new line is found and the buffer isn't full, it returns true, which means partial message received. If the buffer becomes full before a new line is found, the current implementation might return an error or simply wait for the next select cycle. The key is that the message is read incrementally across potentially multiple read calls. Back in the server loop, after reading, we repeatedly call getMessage, which is over here. This function searches the buffer using the find network new line again for a complete \r\n terminated message. If it founds, it allocates memory for the message, copies it out, and importantly uses memmove to shift any remaining data in the buffer, which is part of the next message perhaps, to the beginning. This prepares the buffer for the next read. Now, some of the pros and cons of this approach. One of the pros is that it handles network fragmentations really well. TCP doesn't guarantee message boundaries, and this approach currently reassembles messages based on \r\n delimiters, even if they arrive in pieces. One of the other pros is that it uses a fixed size buffer per client, which simplifies memory management compared to dynamically resizing buffers. One of the cons of this approach is that a single logical message segment, a text between \r\n delimiters, that is itself longer than buff size, cannot be reading, potentially leading to a data loss or client disconnection for a specific message. The protocol effectively imposes maximum message segment length limited by buff size. Another con is that malicious or misbehaving clients would send data without new line, filling the buffer and potentially causing denial of service for client connection until a timeout or error occurs. As for the conclusion, we demonstrated code compilation, background process management, signal handling, and the client message reception mechanism. and everything works well. Thank you so much for watching.